welcome everybody. So today what I'm going to talk to you about is the last part of bonding, and that is types of solids. And so we sort of alluded to these types of solids, but there's some that we didn't really discuss at all, particularly network and metallic. So we're going to talk about all four types of solids today, and we're going to kind of put them into perspective in terms of the bonding. And so the first type of solid is an ionic solid, and this we really discussed when we did ionic bonding. And so this is just sort of like, well, what does ionic bonding result in? It results in a substance that is normally a solid at room temperature, and that solid tends to have the following properties. It tends to have these high melting points. It tends to have low conductivity when it's a solid, but when you place it into water or you melt it, those ions that are stuck together in the ionic solid will split apart, and they're free to move, and they can conduct electricity. So that's down here when melted, and this is because of the mobile ions. Now, why do they have these properties? Well, these ionic compounds, they consist of these positive and negative ions. And those positive and negative ions, they are very, very attracted to one another. And that leads to something called a high lattice energy. Generally, ionic bonds are the strongest type of bonds that you will find when you compare them bond to bond. And that's because those types of bonds, ionic bonds, are pure positive and negative ions being attracted to each other. So they tend to have pretty high melting points. What you'll see is that other substances, they also can have high melting points, but it's not due to the exact individual bond strength. It's more of like a strength in numbers type thing. So ionic solids, they relate to ionic bonding. If you look back at the ionic bonding notes, you'll see that, I said the same thing in the beginning of the packet. The next type of solid that I want to talk to you about is metallic solids, and here we haven't really discussed these at all. What a metallic solid is it's these nuclei from the metal atoms, and they are attracted to the valence electrons, and they're holding all of these in place. This is pretty much the only type of solid where you have identical elements, identical atoms, all bonded together. And there's sort of like this mass sharing of electrons, where all of the electrons are shared between all of the nuclei. And this is called the mobile sea. And so, did I write that here? Yeah. All have delocalized electrons, and the electrons are able to move throughout the solid. And this is sometimes called the mobile sea of electrons. And that's because those electrons are able to move throughout all of the atoms. They're free to move. And so when you look at a metal and you're like, oh yeah, it conducts electricity as a solid, it is malleable, it's ductile, it has luster, all of these things go back to the idea that the electrons are able to move. And if I show you what a metallic solid looks like here, do I have one? Yeah. So here's my metallic solid. And what you can see in the metallic solid is here are the nuclei, which I'll highlight in red. And then around them in blue, which I'll highlight in purple, are the mobile electrons, and those electrons are free to move. Now, when we look at this in a more complicated way, there's something called band theory, where we talk about the electrons that are in these orbitals or bands of orbitals, and they sort of all kind of blend together into one gigantic energy level, and the electrons can move throughout that energy level. Now, this happens to be partly because in the metal, when you look at their properties, like, oh, they have, low ionization energy, low electronegativity. Well, when you have a solid metal, then the electrons, they aren't held to any particular atom. They can move between the different atoms. Okay, the last two types of solids are both covalent in nature. So both of these have covalent bonds. The molecular solids have covalent bonds, and the covalent network solids obviously have covalent bonds. Now, they both have covalent bonds, and yet they are vastly different from one another. The molecular solids, their properties are defined by their intermolecular forces. And we went over all these intermolecular forces. We have the hydrogen bonding. We have the dipole-dipole. And we have the London forces. So we have these three types of forces depending on if the molecule is very polar, like we have in water, and you have hydrogen bonding, kind of polar, where you have dipole-dipole, or then non-polar, where you'd have London dispersion. And when we look at their melting points, we see that they're generally low. Non-polar, where you have these very, very weak forces, their boiling points are really, really low. These are freezing points, excuse me. Their freezing points are really, really low. And then when you look at polar molecules, well, you can see that they are generally higher than what we have over here. So the intermolecular forces, they're much weaker than an ionic bond or a metallic bond. So even though some people will say, oh, hydrogen bond, it's a strong intermolecular force. Well, it's strong for an intermolecular force, but it's still, in comparison, weak to a metallic bond, a covalent bond, or an ionic bond. It doesn't have the same strength. So molecular solids, they tend to be soft because they have weak forces. They tend to have low melting points, low boiling points. They don't have any mobile ions or electrons to conduct electricity, so they won't conduct electricity. Okay, the last type of solid I want to go over with you is the covalent network solid. And this is one that we haven't really spoken about at all. But a covalent network solid is exactly like it sounds. It's a network of atoms covalently bonded to every other atom around it. So you end up with this sort of structure where it is connected by covalent bonds throughout the entire structure. There's no intermolecular forces. There's no separate particles present. So we don't have any types of intermolecular forces. We just have strong covalent bonds. And what results is things like diamond, graphite, rock, which is silicon dioxide, quartz, Si, silicon carbide. So there's a whole bunch of these. Notice something important about them, they generally have a group 4 element in them. Graphite and diamond are just pure carbon. So when I look at these, here's diamond, and it's showing, if I highlight this, here's a carbon atom, and then it's bound to every other carbon atom around it. Here's another one, bound to every other carbon around it. And so you get this gigantic network of covalent bonds. And this results in very unique properties for these network covalent solids. Particularly, what we see is that in diamond, for example, you have very, very hard substances. Diamond is probably the hardest substance that is known that naturally occur. Rock, another really hard substance. This is due to this strength of bonding within this network. Here we have strength in numbers. We have a lot of atoms. They're all bonded together. An individual carbon-carbon bond, not that strong. But when you have, so many of them, there's strength in numbers. Now here's another interesting case for a network solid. This one is graphite. And graphite's interesting because even though it's a network solid, it's really soft. It has a high melting point, but it's really soft. And that's because the network of the carbons are in these sheets. And it's relatively easy to basically shear off one of these sheets. And if you've ever written with a pencil, which all of you have, when you write with that graphite in that pencil, then you are actually taking off layers of carbon atoms, and they are sticking electrostatically to the page. You want to remove them? Well, then you use an eraser and you remove them. So that is the graphite different. Now graphite also, something cool about it is that between the different sheets here, there are what is known as delocalized, and we've used that term before, delocalized pi-bonded electrons. Those electrons can move, and so people can use graphite, this covalently bonded compound, for electrical conductivity. They use it as electrodes. And that's something that's really interesting about graphite. So, there's always exceptions here. Graphite is one of those exceptions. Here's a covalently bonded network solid that can conduct electricity. It's a common question used on SAT chemistry, and you might see it on your test too, so make sure you know that fun fact. All right, here is just a summary page of all the types of solids. So the type of solid, molecular, what it's made up of, what are the forces between it, what are the properties, what are some examples. And I go through the different network, covalent, ionic, metallic, the different kinds of solids, what the unit is that's connecting them, what the force is, what the properties are, and what the examples are. This is a good summary review sheet. All right, so I've said all I need to say about bonding for you this year. This is a huge chapter. It's 55 pages long. That's pretty crazy. But, you know, it also is probably the central unit to everything that we do in chemistry. Understanding bonding is really, really important. All right, thanks for watching.